Hello geometry friends, welcome to chapter 2 where we skipped section 2.1 and we start with section 2.2. And actually 2.2 and 2.3 go really well together, so we often link them together. And we're getting closer and closer to developing our proofing skills. How do we write a good proof in geometry and use logic to make a statement or an argument? And we start with the basics. So here is section 2.2 and 2.3, friends. This is all about things that we call if-then statements. And these are things you probably use every day, you just don't realize it. If I don't get a chance to eat all my vegetables, then I cannot have dessert. If it's raining outside, then I will have an umbrella. Stuff like that we talk about all the time. Here's a good example here. If it is raining outside, then the ground is wet. That's a really good example of an if-then statement. Sometimes if-then statements are true, sometimes they're false. So we're not always sure. But the if starts out the question and the then answers it. So the then is kind of waiting on the if to see what it says. So overall, it can be called an if-then statement. It can also be called a conditional. We'll use that word sometimes too. So a conditional statement is the same thing as an if-then statement. Or simply, let's just shorten and call it a conditional. Now, in general form, we can use letters P's and Q's. Why? That's just the way we do it in math. So let's just love it. If a P happens, then some Q happens. If P, then Q. So again, P is sort of the question, or we call it sometimes the hypothesis. If something happens, ... And what concludes it is what would therefore be called the conclusion. If something happens, then our conclusion happens. And conclusion is Q. So P is the hypothesis, and Q is the conclusion. If P, then Q. If the hypothesis happens, then the conclusion happens. So here's a good example for our first here. If 2x minus 1 equals 5, then x equals 3. Now, that's actually a true statement too if you actually solve it for x and do the math, but that's not the point. The point is, do you recognize that this is an if-then statement, right? That's an if-then. That's a conditional statement. So let's see, can we find where the hypothesis is and where the conclusion is? Okay, if the formula up you see up here was if P, then Q, the P, the hypothesis, always follows the if. So here is my hypothesis. Not the if. You don't include the if. The if is a clue to show you where the hypothesis is, but the only hypothesis is 2x minus 1 equals 5. If hypothesis. The conclusion follows the word then. Then conclusion. X equals 3 is our conclusion. And there you go. That's a good example of a conditional statement or an if-then. Now sometimes we want to switch it around a little bit. It's not just if this happens, then this happens. Sometimes we're going to go backwards and we'll rewrite it into something called a converse. The converse of an if-then or the converse of a conditional just reverses the letters. Look at this. If this is my conditional, if P, hypothesis, then Q, conditional. Look at the converse. The converse just switches around. If Q, then P. So in a way, I start with the conclusion in a way, and then I end with the hypothesis. Interesting. So we're going to see that if you have a true conditional, if you rewrite it as a converse, sometimes the converses are also true. Not always, but sometimes it is. Let's try. On this first one right here, here's your conditional, here's your if-then statement. If 2x equals 1, 2x minus 1 equals 5, then x equals 3. Like we said on the previous page, this is true. Sure. If you solve that for x, you would get x equals 3. That's a true conditional. That's a true if-then statement. All right, if this is the P and this is the Q, can we rewrite as a converse? The converse would be if Q, this was P, this is Q, so if Q, then P. There's your converse. We just basically moved furniture around. We put if Q, then P. Is this a true statement, friends? If x equals 3, and you plugged into this equation, would this be a true statement? Is 2x minus 1 equal 5? And yes, actually, if you check it and plug it in, it is. That's a true converse. Oh, but not always, though. Not always. And let's check and see. For example, here's a true conditional. If I was born in Orange County, and this is actually Mr. Brown was actually born in Orange County, then I was born in California. Okay, if I was born in Orange County, let's assume this is the Orange County of California. I know there's a lot of Orange counties in other places like Florida, but let's assume that we're talking about California. If I was born in Orange County, then I was born in Florida. True. What's the converse? Could you write the converse? Let's figure out, first of all, where's our hypothesis? I was born in Orange County. There's my hypothesis. There's my P. I was born in California is your conclusion. That's your Q. Okay, if P, then Q. Okay, well again, the original conditional was true. Let's write the converse. Let's do if Q, then P. If I was born in California, okay, then P. Then I was born in the OC. If I was born in California, does that mean I have to be born... Oops, I have to put I was born. Does that mean I have to be born in Orange County? No, not necessarily. Not necessarily. That's false. So some true conditionals, some true if-thens can have a false converse. So they're not always going to be true. Now, all you need to do to show that this converse was false is to use something called a counterexample. Counterexample shows that a conditional or a converse is false. And you only need one. So for example, let's go back to this converse up here. It's false. But why? Can you come up with a counterexample to show why it's false? If I was born in California, did I have to be born in Orange County? No. Where else could I have been born besides in California? I could say I was born in Los Angeles or Sacramento or Oakland or San Diego. But it doesn't mean I had to be born in Orange County. This right here, friends, is a counterexample, and it shows that my converse was false. And you only need one counterexample to do that. So there's your converse. If you have a true conditional, you can have a true converse, just like we did up here with the algebra one. But sometimes you can have a true conditional that has a false converse. And all you need to show that's false is one single counterexample. Good, but let's talk about how else we can notate if-then statements or conditional statements. Okay, the standard one is this one, if P, then Q. And here's a good example. How about this one? If, hypothesis, if 2x equals 6, then, conclusion, x equals 3. That's a true statement. And actually, if you think about its converse is also true too. All right, that's a pretty good one. How about this type? We can say it in this way. This is just basically playing with English. P implies Q. So P happening implies that Q is also going to happen. Having a hypothesis means that you're going to have that conclusion. And let's use the same P and Q that you see above it. 2x equals 6 implies that x is going to equal 3. That makes sense, especially when I put the example in there. Okay, that's another one. This one, next one, is kind of interesting because it puts the conclusion first. But look at the order of the sentence. Q, if P. Meaning Q is going to happen, the conclusion will happen if the P, the hypothesis, happens. Well, that makes sense. Here's your example. Again, using the same ones. X equals 3 is true if the 2x equals 6. All right? I put this last one in parentheses because it is a little confusing, and so don't write it down. I just want you to see that there is another choice. I wonder if you can find out why I don't like this one. Look at the other three. If P, then Q. P implies Q. Q if P. Do you notice that whenever you have an if, what usually follows the if? We're trained to know. It's the hypothesis. It's P. Do you notice here that this one doesn't? And it is another way of writing it, but because of that confusion with the if, I don't like to talk about this one. We're going to put this one away. You go bye-bye in the garbage. So only worry about the first three. And really, really, only have to worry about the first one. That's the most popular. So back to conditionals and converses being true. If a conditional, if an original if-then, and its converse are both true, we can combine them. We can put them into a single sentence that uses both the conditional and the converse together. And we call that a biconditional. A biconditional is a statement that's a combination of its conditional and its converse. But it can only happen if they're both true. If they're not both true, we cannot make a biconditional. If the converse and the conditional are not both true, we cannot make a biconditional. Ooh, look how we notate though. This is so hot. All right, we're going to say P if and only if Q. That implies if P happens, then Q happens. And its converse, if Q happens, then P happens. Or, oh, you want to see this? This is what they use in college. So I'll give you a little heads up. You can talk like you're in college math. See how cool you are. You can say P if and only if. The way we write that in college math is this. Can you see? It's almost like an abbreviation of if and only if. I just put IFF. That means if and only if. So you can write that if you want, folks. See how cool you are. P, if and only if Q. That's a biconditional, and that can be broken down into a true conditional and a true converse. For example, all right, here's our first conditional. If today is Sunday, hypothesis, then tomorrow is Saturday, conclusion. Is that true? If today is Friday, does that mean tomorrow is Saturday? Yes, it does, if we're living on a normal calendar. Let's switch it around. Let's put the conclusion there, the hypothesis there. Ready? If, here's your converse. Ready? If tomorrow is Saturday, then today is Friday. All right, that's our converse. If Q, then P. Is that true? If tomorrow is Saturday, does that mean today has to be Friday? Well, yeah, again, on a normal calendar, yeah. So look what you found, friends. You found a conditional that's true. You found a converse that's true. So can we make a biconditional? Oh, you betcha. And we can take, again, this form that we found up here. You can say the P, if and only if the Q. Notice that the if stuff is on the inside. There's no if in the beginning. So look at this biconditional. Look how we'd write it. We would say, not if today is Friday, we would just jump right into P, if and only if Q. Today is Friday, if and only if tomorrow is Saturday. You could have also written it as tomorrow is Saturday, if and only if today is Friday. Again, that implies that you have a true conditional and a true converse. Good job. Now we have more than just conditionals and we have converses, but I just want to play a little bit more. Some good, fun, real-life examples. Ready? Here's your conditional. Let's figure out if these are true and false. Nope. Before we do that, actually, we do need to learn what is out there besides conditionals and converses. We have two more, folks. We have something that's called an inverse and something called a contrapositive. I almost got ahead of myself. I was too excited. All right, here's your conditional. Ready? Conditional. If P, then Q. Done. P is the hypothesis, conclusion. We know that. Good. Converse. You know this. We flip it around. If Q, then P. Now, when we start doing inverses and contrapositive, look at the big clue word right here. We start doing the opposites. We start doing the nots. And look and see. Can you just read what the inverse is? And what is that really closely related to up above? Can you see? It actually is like the conditional, but just not. It's like the opposite of the conditional. Not switched, but just opposites. If not P happens, then not Q is going to happen. All right, so to find the inverse, you take the conditional and you make it opposite. If not P, then not Q. All right, take a look at the contrapositive. Look at the form of that. What does that look the most alike from above? Doesn't it look like the converse? But again, just the opposites. Converse is if Q, then P. So the contrapositive is if not Q, then not P. You took the converse and made it opposite. All right, these are four really hard words to memorize. How do we know what is what? Well, the conditional is always the start. It's always the if P, then Q. Converse means you're going to convert it. You're going to switch the P's and the Q's. Now, the contrapositive is literally the longest word. So from the conditional, you do the longest stuff, meaning you do more things. First of all, you switch your P's and Q's, and then you add nots. So making the contrapositive from the conditional has two steps. 1, 2. It's got the most work. So associate the most work with the longest word, contrapositive. That's a long word. I got to do a lot of stuff. I got to switch my Q's and my P's, and then I got to make it opposite. Okay, so conditional, off to the side. If P, then Q. Converse, if Q, then P. inverse, it's the conditional but not. If not P, then not Q. And the contrapositive has the most work. We have to switch it and make it negative. If not Q, then not P. Okay? A great way to illustrate all four of these vocab words is with something called a Venn diagram. Have you seen this before in math? Venn diagram was sort of invented and utilized a lot by Mr. Venn. And what he did is he was showing logic here. He'd take a larger area, like a circle, and he's going to call that Q. Everything in that circle is related to Q. And then put a smaller circle inside and call everything in that circle P. So look at our conditional and look how this circle Venn diagram is actually pretty cool. If P happens, if you have a point P, can you see that because he's inside the larger circle here, if P happens, then Q must happen. Because P is inside of Q. So if you pick a point that's inside of P, do you see that you've also picked a point that is really still inside of Q, because Q is around the whole thing? That's interesting. Let's try the converse. How does the converse look in a Venn diagram? Well, let's see. The converse says, if Q, then P. So let's draw a point that's in Q. How about here? Then P. Oh, now wait. That point that I just drew is in Q. Is it in P? No, it's not. So interesting. Remember we said you can have a true conditional, but maybe the converse is not always true. If Q doesn't always mean that you're going to find a point that's in P, according to this Venn diagram. Could you find one though? Could you pick a point in Q that is also in point P? And I think I found it right here. This point right here is in Q. Oh, and he's also therefore in P. So you can find a place and a way to make the converse true, but it's not always going to be true. Let's look at the inverse. The inverse says, if not P, meaning, can I draw a point that's just not in P at all? Nowhere here. Okay, I can draw a point right here. That's not in P. The inverse says, if there's a point that's not in P, then it's not in Q. Well, look at this point. This point is not in P, but it is in Q. So maybe sometimes the inverse isn't always true. Can you guys think of a point that I could draw that's not in P and therefore would also not be in Q? I guess the only way would be to draw it outside of Q. That purple point is not in P and it's also not in Q. So the inverse is also not necessarily a true statement. Last one, contrapositive says, if I have a point that's not in Q, then he's not in P. Ready? If you draw a point that's not in Q, it means he's not here at all. Let's put him out here. That's a point that's not in Q. Can you see that there's no possible way that he could be in P? So we're going to talk a little about this later, but can you see that if the conditional is true, the contrapositive is always true, right? If P then Q here in the Venn diagram does mean that if you have a point that's not in Q, he also will not be in P. So the contrapositive is also true. Interesting. All right, let's play more though. Okay, here's our example that we were talking about before. All right, think about this. Here's your conditional, friends. If I can hear the TV, there's your P, then it is turned on. There's your conclusion Q. There's your conditional. If I can hear the TV, then it is turned on. Now, let's assume these are normal situations. In a normal situation, if you can hear the TV, friends, does that mean it's turned on? I sure hope so. If not, then you just need to get more sleep because you are going crazy. So yes, that's a true statement. All right, how about the converse? Converse, remember, we're going to flip these and do if Q, then P. Okay, let's read this and let's see, is this a true statement? If the TV is turned on, then I can hear it. If a TV is turned on, friends, does that mean you always can hear it? No, not always, not always. Now you just proved something false. Can you think of a good counterexample? A good counterexample would be, well, maybe the TV is on mute. Okay, cool. How about the inverse? Okay, for the inverse, remember we're going to take P but make it not, and we're going to take Q and make it not. Okay, if the conditional was if I can hear the TV, then it is turned on. The inverse says if I cannot hear the TV, then it is not turned on. That would be the inverse. If not P, then not Q. Is this a true statement, friends? If you cannot hear the TV, does that mean it's not turned on? No, not necessarily in a real world situation. Again, you can use the same counterexample. You can say, well, maybe the TV is muted. You can say maybe you're in a different room, or the TV is in a different room and you just can't hear it. So that's one counterexample that proves it false. Ooh, did you notice that the converse and the inverse have the same truth value, meaning if one was false, the other one's false? That's pretty important. We'll come back to that in a second. Let's go to the contrapositive. Here we go, folks. Contrapositive, remember that is if Q but the not, and if P but not. Okay, that's the contrapositive. If not Q, then not P. Let's actually take a look at this. If the TV is not turned on, then I cannot hear it. Is that true in real life? Again, as long as you're getting enough sleep, folks, that should be a true statement. So what can you guys say about the conditional and the contrapositives? If one is true, the other one is typically going to be true. That's kind of important because we're going to call now that the conditional and the contrapositive are always what we say logically equivalent, meaning equivalent meaning equal, and logically talking about true or false. So if the conditional is true, then the contrapositive is true. Always. They're always linked together, the conditional and the contrapositive, always. If one of them is false, oh, I bet you the other one has to be false because they're always logically equivalent. And like you said up above, you can see that that same thing happens with the converse and the inverse are also logically equivalent. If one is true, the other one is always true as well. Okay, and here's another example of a Venn diagram, this time with Q and P. If Q means yes, then P. If you pick a point in Q, then you pick a point in P. All right, let's put it all together. What can we conclude? If I give you a statement, first, can we put it into an if-then conditional? Because right now, this is kind of generic. All runners are athletes, but that's not an if-then statement. But we say it that way normally. Can you rewrite it? How about this? If a person is a runner, so we had to add the word person here to define it. If a person is a runner, then they are an athlete. That's basically what you're saying here in the circle. All runners are athletes. Well, that means if you're a runner, then you're an athlete. So we're going to write it as a conditional. If P, then Q. So what I'm going to do is I'm going to try to throw things at you. I'm going to figure out what can you conclude. Let's assume that all runners are athletes. Let's assume that's a true statement. Then what can you say about number one? Mrs. Davis is a runner. Now first, do you notice what I did with this conditional is I made a Venn diagram. Remember that the P was on the inside and the Q is always on the outside of a true Venn diagram. And remember the P here is if person's a runner, that's my P, so I put it here, runners. Then they are an athlete. This is my conclusion, that's my Q, so I put Q outside here. Okay, so P is always on the inside and Q is always on the outside. Let's figure out, what if Mrs. Davis is a runner? Let's put that dot. Where could Mrs. Davis be? If she's a runner, she really has to be here, right? That means if P. Well, if she's a runner, then you can say that she is, obviously, there's nowhere else to draw that point. She must be an athlete, right? She is an athlete. What is that? If she's a runner, then she's an athlete. What are we using? This is the original conditional. This is if P, then Q. And that's what you concluded. How about number two? Mr. Brown is not an athlete. Oh, that's such a true story too. So if Mr. Brown is not an athlete, all right, let me erase where Miss Davis was. If I'm not an athlete, where can you put me in this Venn diagram? I am not an athlete. The athlete is the entire outer circle, right? If I'm not an athlete, I cannot be in that circle. Let's put myself over here. All by myself. Thank you. Thank you very much. Buy my CD. So that's on the outside. If I'm not an athlete, what can you say? Because I'm not an athlete, could I be a runner? No. There's no way that I can write myself as not an athlete and also be a runner. It's not possible. Because once you're a runner, you are inside the circle of athletes. So what can you conclude? You conclude that Mr. Brown is not a runner. Now, what did I just make? I am not an athlete. An athlete was Q. So I'm saying if not Q, you concluded with not a runner. Runner was P. Which one is if not Q, then not P? You just found the contrapositive. The contrap. Okay? If not Q, then not P. All right, number 3. Miss Spadero is an athlete. And she is. She's a very good basketball player. So let me erase here. Let's get a little bit of room here. Erase my circle. Erase Mr. Brown, the unathlete that he is. All right. So Miss Spadero is an athlete. Where can I put her? If she's in an athlete circle, she could be here or here, anything like that. Oh, but wait, I could put in here too. Because these dots here are also in the athlete circle. So do we know for sure, if she is an athlete, do we know for sure, is she absolutely a runner? No, we actually don't. She could be. We can put them here. She's an athlete and therefore a runner. But I could also put dots here. This is also, Miss Spadero is an athlete. Does that mean she's a runner? No. So conclusion? No conclusion. This one has no conclusion. She could be a runner or she might not. Look at what form this one is. Miss Spadero is an athlete. Athlete was Q. She was saying if Q, well, if P can give you Q, that's your conditional, and that's true. Does that mean that Q gives you P, the converse? Does that mean it's always true? No, we learned that before. So it looks like I was about to start a converse. Remember, a true conditional doesn't always give you a true converse. And that was a great example of it. Just because Miss Spadero is an athlete doesn't mean she's a runner. Do you want a counterexample here? What else could she be if she was an athlete but not a runner? She could be a gymnast. She could be a swimmer. So lots of different choices. All right, last one here, friends. Mr. Stone is not a runner. If he's not a runner, where could I put that dot so that he's not in the runner's circle? Could I put it here? Sure. That means if he's not a runner, is he an athlete? Yes. Sure. Oh, but wait. If he's not a runner, can I put him out here? That's also not a runner. Does that mean he's an athlete? No, he's outside the circle. Ooh, so we found 2 different versions. That's interesting. So is there a conclusion? If you say Mr. Stone is an athlete, does that mean he has to be a runner? No, we don't know. Again, no conclusion. So the Venn diagram helps, but also you can realize what form we're talking about. We're saying Mr. Stone is not a runner. Runners are P. You're saying if not P. Remember, not P going to not Q. Remember that form? That was the inverse. And the inverse might also not necessarily be true. These are right now logically equivalent. Can you see? The converse and inverse are both no conclusion, while the conditional and the contrapositives were both true because they're logically equivalent. Pretty heavy stuff, but using this kind of logic is going to lead us closer to making proofs so we can logically argue why things are happening. Why are triangles congruent? Why are angles congruent? All that kind of ideas. So we usually start with an if and we conclude with a then. There's your introduction to logic, friends. Hope your brain is not too fried, but you got a great start on conditionals, converses, inverses, and contrapositive. Great job, everybody. We'll see you next time.